Okay, hello everybody. Welcome to the 6th lecture. We'll start with a short overview of what we have accomplished so far. We started with an overview of physics, where we saw that there is classical physics and it has some shortcomings. And from those shortcomings were resolved partially by two relativity theories of Einstein and quantum mechanics. And then we went over the main ideas of classical physics and discussed two important tools to go to the modern physics is tensors and variational principle. And the last lecture, we started to discuss the Lorentz transformation. So let's see what we have done on the last lecture. Lecture 5 was Lorentz transformations. And in this lecture, we have shown that based on the same principles we had in classical physics, the principle of relativity, we can show that the transformation between two inertial frames are linear in the space-time transformation. And by choice of the axis of the symmetry to keep the symmetry, not to break the symmetry which is inherited in the problem, we can add more information about this transformation, leaving us only with one free parameter, which this free parameter can be identified if it is chosen to be 0, we got the Galilean transformation with the meaning t equals t prime, and some parameter there a equals 1. And we have shown that this assumption is not necessary. Logically, you can assume it is not so, because you are comparing two different things, time on one clock and space-time transformation on the other system. We have shown that in this case you have an invariant metric, and we found it, and this metric is universal, independent on the transformation between the two systems. We found very interesting that now the velocities are bounded by some universal velocity, which was not the case in the classical case. In classical case, velocity by any vector in R3. And now you have a limitation. This limitation causes you a different geometry, non-trivial things, a lot of things that we'll discuss today. We found out these transformations define your velocity addition or mainly composition. And from this addition, we were able to resolve two shortcomings of the classical physics. The first one is that the speed of light is independent on the velocity of the source. This resolved as the Michelson-Morley experiment, which couldn't be explained within classical physics. And then also we found that the Fizeau experiment describing the velocity of light in moving water, which had very strange formula, could not be understood within classical physics. Using the right velocity addition, we got the right formula. And it's not surprising that both things we found were related to velocities close to the speed of light. And therefore, there we could see the difference between classical and relativistic and Lorentz transformation. Classical one, which is based on Galilean, and the Lorentz one. We have found also application for one important device, fiber optic gyroscope, which is very important to define the rotation with respect to an inertial system, which is based on Sagnac effect. And we've seen that really behind this device is the relativistic formulas for velocity addition. If they are done properly, you obtain the right formula for the this effect, Sagnac effect, and which is used for the fiber optic gyroscope. Asks this car to prepare some exercises on this lecture, and I'm transferring him now the podium. Okay, see, you can.
Okay, hello everybody. And here are some exercises which Jakob and I developed, which we hope will increase your understanding of the Lorentz transformations and the Einstein velocity addition. Okay, so the first problem is to understand the physical meaning of the various components of the Lorentz transformation. Here we're taking the Lorentz transformation in what's called standard configuration, which means we do not reverse the axes. All the axes are parallel. And we're also using CT instead of just T. This makes the dimension of each component the same length and makes the matrix of the Lorentz transformation symmetric. Okay, so let's take K to be an inertial frame on Earth, what we usually call the lab frame. And we'll take K prime to be the flame of an airplane flying at constant velocity. So the airplane flies and it crosses two lighthouses at different times. And in the plane, he measures this time difference to be T prime. And T, which is the result of the Lorentz transformation, is gamma T prime. The time difference measured in the airplane gets multiplied by the gamma factor. This is normally referred to as time dilation. This gives you the time difference in the lab frame on Earth. And X is gamma VT prime, is the distance measured on Earth between these two lighthouses. If you compute dx dt prime, you'll get gamma V. So this is some new kind of velocity where the distance traveled is measured in a different frame and the time is measured in your frame. This gives you your proper velocity with respect to another frame. Now to understand the second column in the matrix, consider two simultaneous events in the airplane, which are separated spatially by distance x prime. Then T, which is L1 to x prime, it will be not zero, but represents the time difference of these two events in the lab frame. So these simultaneous events in K prime are not simultaneous in K. This is called the relativity of simultaneity. And finally, the last component on the bottom right transforms the spatial separation between simultaneous events in K prime to their spatial separation in K. Okay, the next problem from linear algebra, take this standard configuration Lorentz transformation, find the eigenvalues and the eigenvectors. We do the standard thing, determine an L minus lambda I, and you get this polynomial in lambda, which solves easily, and you get gamma 1 plus or minus V over C. For the lambda with the minus, the eigenvector is easily calculated by substitution for S to be 1 minus 1. And for the other eigenvalue, it's also an easy calculation. The eigenvector is 1, 1. Let's see this visually. Here we have the t and x-axis. We're looking at, it's called one-dimensional space-time, like 1 plus 1 dimension, 1 space dimension, 1 time dimension. And the lines x equals t, x equals minus t represent the light cone. And E0 is a unit vector in the t direction, E1 is a unit vector in the x direction. What does the Lorentz transformation do to these vectors? So E0 is rotated to the right and stretched, and E1 is rotated this way. So the axes are no longer orthogonal. Vectors on the light cone, like this is an eigenvector for the plus eigenvalue, and he remains on the light cone and gets stretched. The other eigenvector on this part of the light cone is shrunk, and that's because the relative velocity is in the x direction. Here's a problem I took from Rindler's book. A spaceship travels to a star that's 8 light years away, and when they get there, they see the clock has moved 8 years. So what is the ship's speed relative to the Earth? So here's this same standard configuration Lorentz transformation. Earth is the lab frame with the unprimed coordinates, and the spaceship is prime coordinates. So let's look at the calculation of this. X is gamma vt prime plus x prime. Now t prime is the time measured in the spaceship, and they say 8 years have passed. X prime is the location of this clock, which is we can take arbitrarily to be the origin. And x is the distance to the spaceship as measured from Earth, which is 8 light years. So plug everything in, you get 8 light years equals gamma v times 8 years. So the 8's cancel, and a light year is 1 year times c, the speed of light. So gamma v equals c. Write out what gamma is, do the algebra, square both sides, and you get that v equals c over square root of 2, which is about 2/3 the speed of light. So notice that it takes light 8 years to get from Earth to where the spaceship is, and that's traveling at the speed of light. They were traveling less than the speed of light, and they also got there in 8 years. How is this possible? It's because it depends on which clock you're using. The clock on the spaceship says 8 years. The clock on the Earth will say about probably square root of 2 times 8 years, which is about 12 or 13. Okay, next problem, the symmetric velocity. Yaakov will speak about this in the lecture, and it's a very useful tool, especially when we go to the informal automorphisms. Now, given a velocity v, you want to find a velocity w such that if you add them together with the Einstein addition, you get v. W is like dividing v by 2 relativistically. So write down what w plus w is according to the addition formula and set it equal to v. So v and w are parallel. Let w be alpha v. Plug in alpha v for w everywhere here. And you do the algebra and you get a quadratic in alpha. This is one root. The other root would make w faster than the speed of light, so we discard that one. This is our alpha. We simplify it down to gamma over gamma plus 1. So we have an explicit way of going from a given velocity to the corresponding symmetric velocity. And here's an animation of what this looks like. The two frames that are moving right and left have a relative velocity between them of v, and the relative velocity of each of these frames to the smaller axis frame in the middle is w, the symmetric velocity. So let's look at that one more time. Okay. And finally, we'll talk about a new parameter, the rapidity. We saw that the Lorentz transformations depend on only one parameter, the relative velocity v between the inertial systems. You can define another parameter, psi of v, defined in this way. So we're going to compute the hyperbolic cosine, sine, and tangent of psi, and write the addition formula in terms of this new parameter. So for the hyperbolic cosine of an inverse hyperbolic tangent is given by this formula, and which is exactly gamma. And the hyperbolic sine of inverse hyperbolic tangent is the v over c over this square root. Straightforward formula for computing these things. And you get gamma v over c. And obviously tangent, the hyperbolic tangent is this one, either by dividing sine by cosine or by just looking at the definition of psi in the first place. Now, how do we use this to write the addition formula? Take u and v parallel and just consider their magnitudes, and we ignore the direction. We know the direction will be, will stay in the same direction. Divide each velocity by c and multiply by c. And then on the bottom, you'll have v over c and u over c. And v over c is exactly hyperbolic tangents of psi of v. And the same thing for u. And on the bottom, 1 plus the product of the tangents. And this is exactly the formula for the hyperbolic tangents of a sum. C stays outside. And now we can see that if you take the rapidity of this sum, which is the rapidity of this, you'll get exactly the regular sum of the rapidities. Okay, thank you.